Hello everyone, and welcome to the Waveshare's ESP32 Arduino Getting Started tutorial. In the previous lesson, we learned how to control digital signals with the ESP32, such as turning an LED on-off and reading a button state. However, the physical world we live in is far more complex than simple on and off. For instance, the brightness of light and the volume of sound vary continuously. To sense these, we need to use analog signals. In this lesson, we will learn how to use the ESP32 to read these analog signals, enabling it to perceive a richer physical world. In electronics, an analog signal is one that varies continuously in both time and magnitude. Unlike digital signals, which are either 0 or 1, an analog signal has an infinite number of intermediate states between any two values. The temperature, light, sound, etc. that we perceive in our daily lives are essentially analog quantities. So, how does the ESP32 read these continuously changing analog signals? This requires a key component, the ADC. ADC stands for Analog to Digital Converter. Its function is to convert a continuously varying analog voltage signal into a digital value that the ESP32 can understand and process. To better understand this, you can think of the ADC as a precision ruler for measuring voltage. The measurement range of this ruler is typically from 0 volts to the ESP32's operating voltage of 3.3 volts. How fine the graduations on the ruler are depends on the ADC's resolution. The ESP32 we are using typically has a 12-bit ADC resolution. What does 12-bit mean? It means this ruler can divide the voltage range into 2 to the power of 12, which is 4,096 levels. Therefore, the range of values our program ultimately reads is from 0 to 4095. This mapping is very intuitive. When the input voltage is 0 volts, the ADC reading corresponds to 0. When the input voltage reaches the upper limit of its measurement range, the ADC reading corresponds to 4095. As the input voltage varies continuously between 0 volts and the measurement upper limit, the ADC reading also changes proportionally between 0 and 4095. It is important to note that not all ESP32 pins support analog input. You need to consult the pinout diagram of your development board and locate the pins labeled ADC. Now, let's get hands-on. This time, we will use a very common analog component, a potentiometer, to provide a controllable, variable analog voltage to the ESP32. The components needed to build this circuit are an ESP32 development board, a potentiometer, a breadboard, and a few jumper wires. Please build the circuit according to the wiring diagram on the screen. A potentiometer typically has 3 pins. We connect the 2 end pins to the ESP32's 3.3 volt and GND respectively to provide its operating voltage. Which pin goes to 3.3 volt and which to GND is your choice. This only affects whether you need to turn it clockwise or counterclockwise to increase the reading. The middle pin is the signal output pin, which we connect to an ADC pin of the ESP32. Here, we choose GPIO 7. With the circuit ready, let's breathe life into it with code. Open the Arduino IDE. Open the code link provided in the video description and copy this code into it. Select the correct board and port. Ensure USB CDC on boot is enabled. Click the upload icon. After successful upload, open the serial monitor. Look! As we turn the potentiometer, the values printed in the serial monitor change in real time. The ADC value ranges from near 0 all the way up to the maximum value of 4095. Besides the serial monitor, we can also use the serial plotter to visualize the data changes more intuitively. Click the Tools menu and select Serial Plotter. You can also click this button. A window with axes will pop up. You will see 2 colored curves representing the data scrolling in real time across the screen. When you turn the potentiometer, the 2 curves representing ADC value and voltage MV rise and fall synchronously. Through the graph, you can clearly observe the magnitude of the 2 values, their changing trends, and the relationship between them. To use the serial plotter, you need to follow a specific printing format. We'll learn about this in the code walkthrough section that follows. Let's analyze this code line by line. First, we define a constant to store the pin number used by the potentiometer. In the setup function, we initialize serial communication to view the results on the computer. Moving to the loop function, these 2 lines are the core code. The analogRead function is used to read the raw ADC value from the specified pin. The default resolution is 12-bit, returning an integer between 0 and 4095. It's worth noting that before calling analogRead, we don't need to initialize the pin using pin mode as we do with digital pins. Next, we used a new function, analogReadMilliVolts. It is actually an extended function provided by the Arduino ESP32 core library for the convenience of developers. We can find it in the official Arduino ESP32 documentation. In the search box, search for this function. Let's look at the description of this function. It provides a more intuitive way to directly read the voltage on a pin, with the result in millivolts, and its internal implementation also includes calibration for more accurate readings. ESP32 is not only compatible with standard Arduino functions, but also offers many powerful extensions. Learning to consult the official Arduino ESP32 documentation is a key skill for your advancement. Finally, let's analyze the printing part of the code. This follows the data format required by the serial plotter. We used two functions, serial.print and serial.println. The difference is, print outputs the content without a new line at the end, while println automatically adds a new line character after printing. By using this structured output, we send strings formatted in a specific way to the serial port, thereby adapting to the serial plotter. The plotter can recognize and parse this format. It follows these conventions. A comma acts as a separator between different data points. In the code, the values of analog value and analog volts are separated by a comma, so the plotter recognizes them as two independent curves. Spaces or tabs can also be used as separators. The format label :value associates a name with its data. The plotter automatically recognizes this and displays the label in the legend. Finally, a new line character marks the end of a dataset. The serial.println function automatically adds a new line after printing its content. When the plotter receives the new line character, it considers the set of data for that specific time point complete and proceeds to plot it. Using this output format not only makes the data clear and readable in the serial monitor, but also allows it to be directly utilized by the serial plotter for visualization. This is an efficient and practical debugging method. In our experiment just now, you may have noticed that when the potentiometer is turned to its maximum, the ADC value reaches 4095, but the printed voltage vort doesn't seem to reach 3300 mV. It saturates around 3100 mV. To understand this phenomenon, you first need to know that the ADC core of the ESP32 itself can only handle a limited voltage range, approximately 1 volt. To measure higher voltages like 3.3 volt, an attenuator is needed. The core function of the attenuator is to extend the overall measurement range of the ADC. It divides the externally input high voltage by a certain ratio and feeds this reduced voltage to the ADC core for conversion. The attenuator has multiple configurable attenuation levels, each corresponding to a different maximum measurable voltage. The Arduino environment defaults to the level with the widest measurement range. For our ESP32S3 chip, the effective and reliable measurement upper limit of this default level is not 3.3 volts, but approximately 3.1 volt. Therefore, when the input voltage exceeds this value, the ADC reading remains at its maximum value of 4095. For our current example, this difference doesn't have a significant impact. However, understanding this helps us use the ADC more accurately and knowledgeably. When you stop turning the potentiometer, you might notice that the ADC reading doesn't settle steadily on a single value. Instead, it fluctuates slightly within a small range, and occasionally there might be larger glitches. This phenomenon is usually caused by noise. The ESP32's ADC is relatively sensitive to power supply noise and electromagnetic interference from the external environment. There are generally two methods to reduce the impact of noise: hardware filtering. Connect a small bypass capacitor in parallel between the ADC input pin and GND. This can effectively filter out high-frequency noise. Software filtering. In the code, perform multiple samplings, discard a few of the highest and lowest values, and average the remaining values to obtain a smoother and more stable result. In most low-demand applications, slight fluctuations can be ignored. However, when you require high-precision readings, you can try using the methods mentioned above. All right, that concludes this lesson. Let's do a quick review. we learned about continuously varying analog signals and their difference from digital signals. We learned that the ESP32 reads analog signals through an ADC. It has a 12-bit resolution, converting the input voltage into a digital value between 0 and 4095. In our practical coding session, we used the analogRead function to get the raw ADC reading and the analogReadMilliVolts function to directly read the voltage in millivolts. We also learned how to format serial output for the serial plotter, enabling data visualization. Today, we learned how to read analog input using the ADC. In the next lesson, we will learn how to simulate the effect of an analog output. Through this, we will be able to smoothly control the brightness of an LED. Thanks for watching, and see you in the next lesson.